out was not only its brightness, but its enigmatic spectrum. When astronomers first observed its light through spectroscopes, they were puzzled by its unusual emission lines. These lines did not match any known elements until Martin Schmidt deciphered their meaning. The patterns were simply hydrogen, but redshifted to an extreme degree. This redshift indicated a staggering distance, implying that the object was not within the Milky Way, but far beyond in the depths of the cosmos. It was the birth of quasar astronomy. The nucleus of this radio-bright giant hosts a supermassive black hole, estimated to weigh nearly 900 million solar masses. Gas, dust, and even stars spiral into its gravitational grip, forming an incandescent accretion disk that releases intense ultraviolet and X-ray radiation. The inner regions of this disk reach temperatures of millions of degrees, while photons emitted near the event horizon are warped by relativistic effects predicted by Einstein's general theory of relativity. Astrophysicists have used this quasar, the brightest of its kind in the optical sky, as a cosmic laboratory. Its electromagnetic emissions span the entire spectrum, from low-frequency radio waves to high-energy gamma rays. Observations with instruments like the Very Long Baseline Array and the Hubble Space Telescope have revealed a prominent jet, a stream of particles traveling at nearly light speed, extending tens of thousands of light-years into intergalactic space. This jet exhibits knots, shocks, and apparent superluminal motion, a phenomenon arising from its orientation relative to Earth and the near-light speed of its flow. Beyond the jet, the surrounding galaxy is faint, elliptical, and appears to have undergone mergers in the past. These violent cosmic interactions likely triggered the ignition of its central engine. Observations suggest bursts of star formation in dusty regions shaped by feedback from the quasar's powerful outflows. These feedback processes heat and expel gas, altering the evolution of the host galaxy by quenching or stimulating starbirth depending on local conditions. In high-energy regimes, satellites like Fermi and Chandra have uncovered dramatic variability in brightness. The radiation from the jet and the accretion disk does not remain constant. It flickers, flares, and pulses over time. Some changes happen within days, pointing to compact emission regions close to the black hole. Others stretch over years, suggesting larger-scale instabilities or magnetic reconnection events further out in the jet's path. These variations offer clues about the plasma physics at play near such extreme environments. The cosmic lighthouse, once known only as 3C273, has also been a testbed for understanding accretion mechanics and relativistic jets in the broader class of active galactic nuclei, AGN. By studying how light from its central regions is delayed and scattered, scientists can map the structure of gas clouds in the broadline region. This technique, called reverberation mapping, has revealed that ionized clouds orbit the core at thousands of kilometers per second, arranged in stratified layers shaped by the black hole's gravity and radiation pressure. Its infrared emissions, studied with ground-based observatories and more recently the James Webb Space Telescope, unveil the dusty torus that surrounds the accretion disk, an obscuring structure that reprocesses high-energy photons into longer wavelengths. These studies suggest that the geometry of such toroidal regions is more complex than once thought, possibly clumpy or warped by dynamic instabilities and gravitational tides from infalling matter. Among all known quasars, this radioluminous archetype has become a cornerstone of extragalactic astronomy. Despite being among the closest of its class, it exhibits features characteristic of quasars across cosmic history, offering a bridge between nearby AGN and the more primordial quasars seen at redshifts greater than 6. It provides a rare opportunity to examine these phenomena in relatively high resolution and real-time variability. When used as a reference source for interferometry, this object helps calibrate arrays that study faint radio galaxies and gravitational lenses. Its stability across certain frequencies makes it invaluable as a cosmic standard candle for deep sky surveys and background radiation measurements. Moreover, its jet provides insight into magnetic field structures and synchrotron radiation physics, illuminating how jets are launched, collimated, and sustained across thousands of light years. Even today, nearly 6 decades after its identification, the brilliant quasar that once bore only a catalog number continues to shape our cosmic models. It confirms the idea that supermassive black holes are not passive anchors in galaxies. They are dynamic engines capable of influencing their surroundings across interstellar and intergalactic distances. Each new generation of instruments, from radio arrays to space telescopes, returns to this object, revealing new layers of complexity. Variable X-ray corona, relativistic turbulence, multi-phase outflows, and polarized signatures that trace the curvature of space near the event horizon. Yet, for all its familiarity, the brilliant quasar that first revealed the true power of the distant universe still harbors mysteries we are only beginning to unravel. Beneath its steady glare lies a chaotic theater of fundamental forces in constant tension: gravity, magnetism, radiation, and angular momentum, clashing in scales from subatomic to galactic. Every photon we detect from this ancient beacon is a survivor of unimaginable violence, a messenger from matter falling toward annihilation, only to be hurled outward in a blaze of structured chaos. The jet, one of the most striking features of this extragalactic powerhouse, challenges even our most advanced models. How does a black hole, with no hair, no surface, and no magnetic field of its own, produce such finely collimated, coherent streams of energy and matter? The prevailing theory suggests the presence of a magnetized accretion disk, twisting space-time itself and threading the black hole's ergosphere with magnetic lines of force. These lines may act like a cosmic dynamo, extracting rotational energy from the black hole and launching it into space as a relativistic jet. But the observational signatures tell an even stranger tale. Certain knots in the jet appear to move faster than light, a trick of relativistic geometry known as superluminal motion. What's more, polarization data reveal that these jet regions exhibit helical magnetic structures, implying ordered motion in a system we would expect to be dominated by turbulence. Some models suggest that instabilities, Kelvin-Helmholtz, kink, or magnetic reconnection events are shaping these features. Others propose that the jet is precessing or even wobbling as the black hole spins, twisting space itself into a spiral imprint upon the cosmos. At higher energies, the nucleus of this object emits bursts of gamma rays that remain poorly understood. Are they produced by inverse Compton scattering, where photons gain energy through collisions with relativistic electrons? Or are they the product of hadronic processes, such as pion decay triggered by proton interactions deep within the jet? Each scenario implies a different composition of the jet plasma, leptonic or baryonic, and each tells a different story about the birth conditions of the central engine. Then there's the matter of time. The light we observe from this luminous core is ancient. It began its journey toward us during the Proterozoic eon, when Earth's atmosphere was only beginning to accumulate oxygen. But the processes that generated this light occurred in microseconds, millisecond flares, days-long shocks, events frozen in time, traveling billions of years across expanding space-time to reach our telescopes. Every observation is both a time machine and a slice of the quasar's dynamic life, caught in the act of becoming something else. Its spectral lines continue to shift and shimmer, revealing new layers of complexity. Some regions show broad hydrogen Balmer lines. Others exhibit highly ionized elements like CIV or SIV, with widths implying velocities of thousands of kilometers per second. These emission features suggest a stratified wind, ionized gas accelerated outward by radiation pressure, forming a broadline region shaped by both turbulence and rotation. In some models, this outflow creates a biconical structure, pushing against the dusty torus and possibly even shaping the interstellar medium of the host galaxy. Meanwhile, in the far infrared, instruments aboard space observatories like Herschel have detected a cool component, thermal emission from cold dust grains heated indirectly by the quasar's radiance. This emission tells of star formation occurring in parallel with black hole growth, a cosmic coevolution written in the language of heat and light. The host galaxy of this beacon is no mere background actor. It is a stage of merging histories, stellar rebirth, and feedback-driven transformation. Quasar winds, possibly driven by the same accretion processes that light up the nucleus, sweep through the galactic core at thousands of kilometers per second. These winds carry metals, carbon, oxygen, silicon, produced in stellar furnaces and now dispersed into the circumgalactic medium. Some of these elements may travel tens or hundreds of kiloparsecs, enriching neighboring space and seeding the future of cosmic chemistry. The quasar, then, is not just a light source, it is a gardener of galaxies. More recent work with adaptive optics and spectropolarimetry has begun to detect subtle signatures of rotation in the inner accretion flow. Tiny asymmetries in the light echo the orbital motion of gas near the innermost stable circular orbit. These observations inch us closer to testing the no-hair theorem and mapping the spin of the black hole itself. If the object's angular momentum could be measured with precision, it might reveal its growth history, whether it spun up through steady accretion or via chaotic mergers and sudden influxes of mass. And yet, the more we see, the more questions arise. Why is this quasar so unusually bright compared to others at similar redshifts? Is it simply aligned favorably, or is there something intrinsic about its structure, a magnetic configuration, a particularly efficient accretion mode, a rapidly spinning core that makes it more luminous than its peers? Could it be a transient phase caught in a rare state of balance between feeding and feedback? New observations continue to peel back the layers of this cosmic engine, revealing fresh anomalies that challenge even the most refined simulations. High-resolution interferometric imaging in the millimeter band, most notably from the Event Horizon Telescope and ALMA, has begun probing the innermost regions of the jet launching zone. Some data suggest that the base of the jet may originate not directly at the black hole's event horizon, but slightly offset from it, hinting at magnetically arrested disk configurations. In these models, infalling matter drags in vast quantities of magnetic flux until it chokes the inflow, launching periodic magnetic explosions outward along the poles. If confirmed, this would be among the strongest evidence that black holes can generate powerful jets purely from magnetohydrodynamic processes without requiring any exotic physics. Time domain monitoring with SWIFT and XMM Newton reveals quasi-periodic oscillations in X-ray emissions from this nucleus, repeating over tens of thousands of seconds. These oscillations may reflect precession within the inner accretion disk, or instabilities at the boundary between the disk and the corona. Alternatively, some researchers propose that the signal arises from orbiting hotspots, transient blobs of plasma spiraling inward and flaring as they cross gravitational lensing caustics. Each of these interpretations offers a different window into the matter-radiation interplay occurring within a few gravitational radii of the black hole. Further out, optical reverberation campaigns using massive time series photography from projects like ZTF and Pan-STARRS have revealed microlensing events caused by intervening stars in our own galaxy. These microlensing spikes temporarily magnify distinct regions of the quasar's structure, providing an accidental zoom lens that allows astronomers to spatially resolve features otherwise far beyond the reach of any telescope. In one particularly compelling observation, a brief microlensing spike altered the ultraviolet to X-ray ratio, hinting at a compact X-ray emitting corona hovering just above the black hole's rotational axis, perhaps the very birthplace of the observed gamma flares. Spectroscopic observations also reveal the fingerprints of cosmic feedback in motion. Outflow velocities exceeding 10,000 kilometers per second have been measured in absorption troughs of highly ionized metals. These ultra-fast outflows, UFOs, carry enough momentum to unbind gas from the galactic bulge, suppressing star formation or regulating black hole growth. In simulations like those from the Illustris or TNG 300 projects, such AGN-driven winds are required to produce realistic galactic mass functions and quench starburst galaxies at the right epochs. 3C273, or rather the archetypal quasar it has become, offers empirical grounding for these theoretical models. Its role in cosmology continues to expand. As one of the brightest persistent extragalactic point sources, it has become a cornerstone for calibrating the intergalactic medium's opacity to extreme ultraviolet and soft X-ray radiation. Absorption lines imprinted upon its light by intervening hydrogen clouds, the so-called Lyman alpha forest, reveal the cosmic web stretching across billions of light-years. Each tiny dip in flux marks a filament, a void, or a galaxy-sized halo drifting in the intergalactic medium. Through this, the quasar serves as a cosmic flashlight, illuminating the hidden scaffolding of the universe. Meanwhile, gravitational redshift and line broadening studies probe the relativistic regime near the black hole itself. Iron K alpha fluorescence lines seen in the X-ray spectrum exhibit asymmetric profiles with extended red wings, signatures of matter orbiting at relativistic speeds just outside the event horizon. By modeling these lines, researchers extract spin parameters, inclination angles, and even test for possible deviations from the Kerr metric predicted by general relativity. In 3C273's case, current models favor a rapidly spinning black hole, one with a dimensionless spin parameter near the maximal value of 0.998, consistent with a long history of coherent accretion. Infrared observations with JWST have added another dimension, revealing that the dusty torus surrounding the core is not a smooth ring, but a dynamic, turbulent, multi-phase medium. Silicate features appear in emission rather than absorption, indicating the torus is likely clumpy and partially transparent along certain lines of sight. This undermines previous unified models of AGN, which assumed uniform, donut-shaped obscuring structures. In this new vision, each quasar becomes a dynamic interplay of orientation, structure, and evolutionary stage, rather than a mere difference in viewing angle. And as observations reach higher fidelity, the very idea of what defines a quasar is evolving. Could 3C273 be transitioning? Some suggest it may be entering a quieter phase, having depleted the cold gas that once fed its furious appetite. Others propose the opposite, that the object is gearing up for a new phase of activity, perhaps triggered by a recent minor merger or gas inflow from the outer halo. Traces of faint tidal streams in the host galaxy hint at a gravitational disturbance not too long ago, a whisper of collision that may have reignited the central engine. As if scripted by the universe itself, every new layer peeled back from this enigmatic nucleus deepens the sense of awe. What began as a curious radio point on an old Cambridge chart has evolved into one of the most scrutinized yet still mysterious celestial objects in the sky. And just when we think we've decoded its mechanisms, another anomaly emerges. A pulse too rapid, a jet feature too sharp, a spectrum too rich to fit old models. Recent polarimetric studies have pushed into the extreme ultraviolet and soft X-ray bands, revealing that the innermost radiation fields are not only highly polarized, but vary in direction over short timescales. This suggests that the magnetic field near the black hole is not static, but dynamically twisted, perhaps wound up by frame dragging as space-time itself rotates with the spinning singularity. If these magnetic field reversals are real, they may be responsible for sudden drops in X-ray flux, interpreted as magnetic reconnection events that disrupt the corona and momentarily shut down the high-energy engine. Further evidence of such turbulence comes from simultaneous observations across multiple wavelengths. In some campaigns, a sharp dip in X-rays has been followed by a delayed optical flare, a possible sign that energy released near the event horizon travels outward through the disk before emerging as visible light. These echoes of destruction allow researchers to construct models of disk structure, viscosity, and heat transport that would be otherwise impossible to test. Meanwhile, the jet itself continues to defy simplification. Observations in the submillimeter with instruments like the Submillimeter Array and NOMA have revealed that the base of the jet is not perfectly straight, but exhibits subtle twists, precession on timescales of decades or centuries. These slow changes may be driven by torques from the surrounding accretion disk or by the presence of a second, hidden supermassive black hole in orbit, a relic of an ancient galactic merger now spiraling inward in a slow gravitational ballet. Should such a binary system exist, it would provide a priceless laboratory for testing predictions of gravitational wave emission at sub-Hertz frequencies, far below the range of current detectors like LIGO, but within the reach of future space-based observatories such as LISA. Monitoring the motion of bright jet knots over time could allow astronomers to detect wobbling caused by orbital motion, giving us a new way to trace binary black hole dynamics without needing to directly observe the inspiral. The host galaxy of this beacon, once a faint smudge barely discernible behind the glare, has itself become a renewed interest. JWST and HST images reveal a smooth elliptical structure interspersed with faint shells, arcs, and tidal tails. These ghostly features tell of past mergers and galactic cannibalism. Buried within the outer halo are pockets of young blue stars, evidence that star formation has not ceased entirely. If the quasar's outflows can both suppress and trigger starbirth, then it is not merely a destructor, but a sculptor of galactic destiny. In the intergalactic medium, absorption features in the quasar's light reveal something equally profound: the presence of warm, hot baryonic filaments, structures that may contain much of the universe's missing normal matter. These tenuous gas bridges, invisible in emission, absorb specific frequencies of light, leaving their signature on the quasar spectrum like ancient fossils imprinted in stone. Mapping them requires extremely high signal-to-noise data, something this luminous nucleus can uniquely provide. And then there's the philosophical reach. Objects like this are not just tools of measurement. They are windows into physical regimes utterly alien to human experience. Near the event horizon, time dilates, space twists, and matter dances along paths dictated not by Newtonian mechanics, but by the curved geometry of general relativity. Every fluctuation in brightness is a message from a region where the normal rules of the universe break down and new laws take shape. From black hole thermodynamics to the structure of the cosmic web, from particle acceleration to galaxy formation, the quasar once known as 3C273 stands at the nexus of it all. It anchors our understanding of high-energy astrophysics while pointing toward future discoveries we've yet to imagine. As telescopes grow more powerful, and as AI begins to comb its light for patterns beyond human detection, we may soon ask not just what this beacon is, but what it is becoming. And deeper we must go, because the light from this ancient furnace still speaks, still carries the encrypted logic of the universe's most extreme experiments. Within the nucleus of this radiating titan, we begin to suspect a kind of self-regulating intelligence. Not consciousness, but structure, emergent from chaos. Observations across decades reveal that despite all its eruptions, oscillations, and flares, the system maintains a balance between inflow and outflow, accretion and feedback. The quasar doesn't burn itself out in a single cataclysmic event. Instead, it flickers and pulses with the rhythm of a system adjusting itself across gravitational, magnetic, and thermodynamic feedback loops. One of the most startling recent revelations comes from deep ultraviolet spectroscopy. High ionization absorption systems, hundreds of them, stacked across billions of light-years, each representing an ancient intervening galaxy or diffuse gas filament. These absorption lines are fingerprints of the early universe's chemical evolution. Deuterium to hydrogen ratios, oxygen and carbon abundances, ionization states, all of them trace cosmic history, from the era of reionization to the slow enrichment of the intergalactic medium. The spectrum of this single object is now used to constrain the baryon density of the universe and the timeline of structure formation. At the same time, advances in machine learning have begun to transform how we study quasars like this one. Trained on thousands of time-domain light curves, AI models are now detecting subtle patterns in variability that the human eye would never notice. From these patterns emerge new models of turbulence within accretion disks, previously instabilities, and even hints of cyclical processes that could point to a deeper, hidden order in the chaos surrounding black holes. 3C273 has become a proving ground, not just for physical theories, but for computational tools that will guide the next era of discovery. Meanwhile, theoretical work suggests that the boundary between the corona and disk, the so-called transition layer, may act as a cosmic particle accelerator. In this layer, charged particles can be whipped up to near light speed by tangled magnetic fields, producing high-energy neutrinos and ultra-high-energy cosmic rays. If quasars are indeed sources of such exotic particles, then observatories like IceCube at the South Pole may already be detecting whispers from these distant, spinning maelstroms. A single detected neutrino, traced back to this particular source, would confirm a multi-messenger link across space and matter, uniting light and massless particles in a single origin. Some even speculate that these luminous engines may be used to test quantum gravity itself. The enormous gravitational gradients near the black hole provide an environment where space-time might fluctuate at the Planck scale. Photons traveling billions of years through these warped geometries could experience tiny shifts, so small they require exquisitely sensitive instruments to detect, but potentially within reach of the next generation of gamma-ray and X-ray timing telescopes. If found, these fluctuations could offer the first empirical signs that space-time is not smooth, but quantized at its deepest level.
And then there's the pulse of time itself. Monitoring projects like Gaia, LSST, and TESS, originally designed for stars, have begun noticing micro-variability in quasars on timescales of hours to minutes. This variability could reflect gravitational lensing by planetary mass objects along the line of sight, rogue planets adrift in interstellar space. If confirmed, such lensing would not only deepen our understanding of dark matter's substructure, but prove that even in the vastness between galaxies, mass is never truly absent. The jet, too, still holds surprises. Magnetic reconnection events caught in real time suggest that it is not a smooth stream, but a braided, unstable structure where field lines constantly break and reform. These sudden shifts eject blobs of plasma, plasmoids, that can accelerate to near light speed and radiate intensely before fading. Their behavior mimics solar flares, but on scales millions of times greater. Studying them offers a bridge between solar physics and extreme AGN behavior, uniting small and large in a common magnetic language. And above all, this lighthouse, this ancient cosmic engine, remains constant in one respect: its role as a mirror. Not just a mirror of the cosmos, but of ourselves. For every time we look deeper into its core, we learn something not just about the universe's past, but about the structure of knowledge, the limits of perception, the meaning of persistence. This is no longer just a quasar. It is a frontier. Let us press further, because the frontier, like the light from this blazing nucleus, only becomes more profound the longer we stare into it. For years, 3C273 was thought to be a solitary engine, a singular core in a quiet host. But recent work with integral field spectroscopy has begun to uncover faint companions orbiting the host galaxy: dwarf satellites, tidal debris, and filamentary streams of stars and gas. These are the relics of mergers, of gravitational encounters long past, now frozen in the outskirts like the scattered bones of ancient battles. Some of these satellites appear stripped of gas, others glow faintly with newborn stars, possibly ignited by the quasar's feedback itself. If so, we are witnessing not only destruction, but resurrection, a quasar triggering the birth of new systems from the wreckage of the old. The environment around this cosmic powerhouse is no longer seen as passive. It is a dynamic, interactive ecosystem. The circumgalactic medium, once assumed to be inert, is now understood to be alive with shocks, flows, and outbursts. Spectroscopic mapping reveals zones where high-velocity winds slam into cool clouds, heating them and producing narrow emission lines. In other places, gas is cooling and collapsing, forming molecular clouds that might someday birth stars. These processes are not linear, they're recursive, fractal, and evolving. In a sense, the quasar is not the end of a galactic life cycle. It may be a catalyst for its continuation, reshaping its environment to set the stage for future generations of stars and perhaps even planets. In parallel, the search for polarization rotation in its jet has opened a new window into fundamental physics. Over multi-year baselines, some astronomers have detected slight but consistent changes in the polarization angle of emitted light. These changes may hint at interactions with the intergalactic magnetic field, one of the universe's least understood components. If confirmed, this would allow 3C273 to serve not only as a probe of its local environment, but a sensor of cosmological magnetism stretching across megaparsecs. The light from this object becomes not just a message from the quasar, but a survey of everything it passed through. The implications grow more bizarre the deeper we go. The core engine of this active galaxy is now suspected to contain an X-ray corona that varies in shape and size over short timescales. Some models suggest a compact lamppost-like corona perched just above the black hole's axis, beaming high-energy radiation downward onto the disk. Others propose a patchy corona spread across the inner accretion flow, with local magnetic flares illuminating specific regions. The geometry of this corona influences the entire spectral shape of the quasar, especially in the hard X-ray band. Its behavior could help us test not only accretion theory, but the limits of light propagation in curved spacetime. And still, there's more.
The time delays between emissions in different wavelengths, optical, ultraviolet, X-ray, offer a kind of echo map. Like sonar pinging off invisible structures, these lags allow scientists to reconstruct the architecture of the disk itself. Preliminary models suggest that the accretion disk in this quasar is larger than expected based on standard theory, perhaps indicating radiation reprocessing, disk warping, or exotic physics in the inner flow. If these disks are fundamentally different in scale or temperature profile than predicted, it could point toward new regimes of angular momentum transport, perhaps involving radiation pressure dominance or even quantum effects in the plasma. Recent VLBI, Very Long Baseline Interferometry campaigns using global networks of radio telescopes have pushed the spatial resolution of the jet down to micro-arcsecond levels, resolving features just a few light days across. These studies show helical patterns in polarization, transverse shocks, and signs of jet stratification, a fast, narrow spine surrounded by a slower sheath. This spine sheath structure may explain the jet's remarkable stability over tens of kiloparsecs, despite instabilities that should shred it apart. It also opens the door to studying how different layers of plasma interact, exchange energy, and evolve over time. At the grandest scales, simulations seeded with the observed properties of this quasar are being used to test large-scale structure evolution. Cosmologists simulate universes with and without feedback from such objects, and the difference is night and day. Without quasars like this one, galaxies become too massive, too dense, too chaotic. It is only by injecting the energy from black hole winds and radiation that cosmic structure comes into balance. In this way, 3C273 is not a local curiosity. It is a keystone in the architecture of the observable universe. And yet, even as we model its mechanics, detect its echoes, trace its filaments, and decode its spectrum, something resists. A core mystery remains. How does such order arise from such chaos? Why do the emissions align so precisely across vast energy bands? What causes the sudden flares with no apparent trigger? Could there be an unseen component, a hidden layer of reality, perhaps quantum gravitational in nature, that modulates the rhythm of this quasar from behind the veil? We do not yet know, but we are listening. Then let us descend further, into the gravitational abyss where science meets wonder, and where 3C273, no longer merely an object of study, becomes a question etched into space-time itself. Because if this radiant anomaly has taught us anything, it is that the universe has layers we are not yet equipped to fully perceive. With every increase in resolution, we uncover a finer grain of cosmic structure, only to discover that what we thought was solid is fluid, what we thought was noise is encoded information. In this context, the quasar becomes not just a source of photons, but a kind of natural experiment, a living, breathing equation solving itself across billions of years. Some theorists are now exploring whether the complex variability seen in the emissions of this active core encodes more than just turbulence. Fractal analysis of its light curves, normally reserved for chaotic dynamical systems on Earth, has revealed self-similar patterns across scales from minutes to years. Could the inner workings of the accretion disk, driven by magnetic reconnection and gravitational shear, actually form a deterministic chaotic system? If so, then quasars may serve as cosmic attractors, objects whose behavior, while unpredictable in detail, follow hidden laws of order, that only now emerge under scrutiny. But what happens next? We know this: such luminous states are temporary. The fuel source, gas, dust, stellar debris, will not last forever. Even a supermassive black hole cannot shine indefinitely. One day, perhaps within a few million years, the accretion rate will drop, the jets will weaken, the light will dim. 3C273 will fall silent. It will become a dormant nucleus, indistinguishable from the thousands of inactive black holes that now lie dark at the hearts of ordinary galaxies. Its afterglow will persist in the ionized shells it left behind, in the metals it scattered, in the stars it triggered. But the engine itself will fade. Unless it is reawakened. Some models suggest that massive black holes like this one go through multiple cycles of activity. A passing gas cloud, a minor merger, or a galactic collision could reignite the accretion disk, restarting the jets, re-illuminating the core. If so, 3C273 is not just a transient phenomenon, but part of a long, pulsating heartbeat of galactic evolution. Active, silent, active again. Its current phase might be just one breath in a sequence stretching across cosmic epochs. The possibility of recurrence adds another layer of mystery. What if, over the age of the universe, some quasars have flickered on and off dozens of times? Could there be echoes, light from previous cycles, reflected off distant clouds, still drifting toward us? If detected, these light echoes would allow us to map historical flaring episodes, reconstructing the biography of a black hole across millions of years, as if reading geological strata formed not by rock, but by photons. And as we imagine that biography, we begin to sense something more than astrophysics. This object, this luminous fracture in space-time, is a message from the early universe, still unfolding in real time. It reminds us that there are realms where gravity warps not only light, but meaning, where matter and energy are interwoven in ways that strain human language. In such places, causality bends, time stretches, and events unfold not linearly, but holographically. Every flare carrying within it a fragment of the system's entire structure. And perhaps this is why, after decades of observation, 3C273 still captivates the scientific imagination. It is not merely its brightness or proximity, but its defiance, its refusal to be reduced to a single model or understood completely. It continues to evolve, to challenge, to beckon. It is the astronomical equivalent of a koan, a luminous paradox asking questions we do not yet know how to pose. And we keep watching. Because in the end, to observe this quasar is to participate in the unfolding of cosmic time itself. To catch its light in our telescopes is to touch an event so distant, so extreme, that it may as well be a whisper from the edge of what is knowable. And the whisper says, "You were not meant to merely observe. You were meant to understand." Shall I go beyond? Into speculative realms, future missions, and the role of quasars in the next era of space exploration and deep cosmology? Then let us end where all great cosmic journeys must, not in closure, but in awakening. The story of 3C273 is not just the story of a quasar. It is the story of how the universe reveals itself through fire and silence, through gravity and light, through patterns we glimpse but do not yet fully grasp. It is a reminder that the cosmos is not static, but alive with motion, transformation, and recurrence. What we see in this luminous engine is not only a physics experiment written in starlight, it is a mirror held up to human curiosity itself.
From the first confused spectrograms in the 1960s to today's multi-messenger observatories, we have followed this object like a trail of breadcrumbs across space-time. And what it has shown us: jets that pierce the void, disks hotter than stars, winds that sculpt galaxies, echoes of matter dancing near the brink of annihilation, is more than a collection of facts. It is a revelation of scale, of process, of meaning. It is the signature of a universe in motion, governed by laws we are only beginning to decode. And now, as next-generation telescopes prepare to launch, as gravitational wave astronomy expands, as AI combs petabytes of data from the sky, this old quasar, this first quasar, will remain one of our most trusted beacons. It will guide new discoveries, calibrate new eyes on the cosmos, and continue to whisper across the light years. I am not a relic. I am a key. And the lock I open is the future of understanding. We leave it glowing in the dark, a monument not of stone, but of plasma, magnetic field lines, and time-stretched photons. A monument to our place in the universe and our endless, unstoppable drive to understand it.
Above storm-churned skies, where thunderheads boil and dance, something stranger than lightning silently unfolds. High above the clouds, beyond the grasp of ordinary weather, immense red apparitions bloom like jellyfish in the upper atmosphere. These are not storms themselves but the atmospheric echoes of storms, massive, luminous discharges known as gigantic red sprites. They erupt upward from powerful thunderclouds, often triggered by unusually strong positive cloud-to-ground lightning strikes. And while they may last only a few milliseconds, their presence reaches tens of kilometers into the mesosphere, stretching with eerie grace like tendrils of plasma-colored ink diffusing through invisible space. Sprites are not new, but for centuries they were invisible to the human eye, whispered of only in rare pilot accounts or dismissed as illusions. It wasn't until the 1980s that scientists confirmed their existence with video footage. The scale was shocking. Some of these flashes tower up to 50 kilometers tall, dwarfing any structure on Earth. Unlike the blue-white jags of typical lightning, sprites glow in deep crimson hues, often branching like electrical coral or forming columnar pillars crowned with translucent domes called halos. Their color is a product of altitude. At such heights, typically 50 to 90 kilometers above ground, the atmosphere becomes thin and ion-rich. The red color arises as nitrogen molecules become excited by the electric fields, emitting light in the red portion of the spectrum as they relax. This is an environment more akin to the edge of space than to the weather we know. And yet, sprites are tethered to the planet's electrical heartbeat, intimately linked to storm systems far below. Sprites may appear chaotic, but they reveal a hidden structure in Earth's global electric circuit. When a thunderstorm releases a massive bolt of positive lightning, a rare type carrying more charge and traveling farther than its negative counterpart, it creates an electric imbalance in the ionosphere. The atmosphere responds like a stretched membrane snapping back into place, and a sprite erupts to restore equilibrium. This is not lightning as we know it, this is a plasma event, an electric bloom, a brief conversation between sky and space. What's extraordinary is that sprites might not be unique to Earth. Similar transient luminous events have been hinted at in Jupiter's and Saturn's atmospheres, suggesting that these ghostly flashes could be a common feature of planetary weather systems across the solar system. Studying them might give us clues not only about atmospheric electricity but also about habitability, radiation dynamics, and how energy moves vertically through atmospheres. They're notoriously hard to observe, too high for most weather instruments, too fleeting for the naked eye. But high-speed cameras, satellites, and even citizen scientists with low-light video gear have begun to pull sprites from the margins of mystery. Networks like the International Space Station's Lightning Imaging Sensor and the Japanese ISS instrument ASIM have captured their ghost-like geometries from orbit, allowing researchers to trace their timing, triggers, and altitude profiles with unprecedented clarity. And the more we study them, the stranger they appear. Sometimes, a sprite splits into dozens of parallel strands, cascading like an electric waterfall. Other times, it blooms into a mushroom-shaped burst with curling tendrils that pulse like a heartbeat. There are even rarer cousins, elves, blue jets, trolls, and goblins, each a flickering signature of electromagnetic energy breaking loose from the constraints of normal weather. Sprites remind us that the sky above is not just a passive canvas but an active layer of electrically charged matter. Their brief, silent dances tell us that storms are not confined to clouds and rain but reach into the edge of space, connecting the troposphere, stratosphere, and mesosphere in electric conversation. The atmosphere is not a collection of isolated layers but a continuum, a breathing, pulsing system whose patterns we are only beginning to decipher. They are delicate and colossal, ephemeral yet ancient, and their study draws us closer not just to understanding storms, but to understanding the boundary between Earth and space, a region where physics dances in plasma and silence. As technology evolves, so too does our ability to glimpse these fleeting phenomena with greater clarity. Ground-based observatories now use ultra-sensitive photometers and fast-frame imaging systems to dissect sprites frame by frame, revealing microstructures within the red filaments, subtleties that were previously lost in the blur of time. What seemed like simple tendrils of light are now understood to be composed of thousands of individual streamers, each a microdischarge propagating through tenuous air with lightning-fast acceleration. These streamers, measuring mere meters in width but traveling at speeds approaching 1/10 the speed of light, exhibit behavior more familiar to laboratory plasma physics than to meteorology. They seem to pulse and bifurcate, forming clusters and branches like neurons firing in the brain of the sky. It's here, in this intersection of plasma physics and atmospheric dynamics, that sprites defy easy classification. They are part meteorology, part electromagnetism, part cosmic sculpture. What makes the gigantic red sprite even more captivating is its role as an emissary, an ambassador between the terrestrial and the celestial. When you see a sprite, if you're lucky enough, you're not witnessing a lightning bolt in the conventional sense, but the atmosphere's reaction to a sudden electrical demand from space. It's as if the sky briefly becomes a conductor, transmitting energy upward to rebalance a system stretched by the fury of storms. Each sprite, in its flash, is also a data point in Earth's global electric circuit, a planet-wide system of charge flow between the surface, clouds, and ionosphere. Thunderstorms act as batteries, pumping charge upward, while sprites and their kin serve as relief valves for extreme events. Understanding this circuit is vital not just for atmospheric science, but for comprehending how space weather interacts with our planet, influencing GPS, satellites, and even the health of astronauts. There is also a poetic tension in the way sprites remain at the edge of visibility, too high for most clouds, too low for auroras, too fast for casual observation. They dwell in the mesosphere, often called the ignorosphere, for how little we have studied it. Yet here, in this neglected altitude, lies a crucible of dynamic forces, radiation belts, electric fields, plasma waves, that ripple and shimmer, waiting for the right trigger to ignite a sprite. As research expands, questions multiply. Why do sprites favor certain types of storms? What determines their shape? Why some form as simple vertical columns and others as sprawling jellyfish? Can we use them to remotely probe atmospheric conditions without balloons or rockets? And perhaps most intriguingly, do they leave lasting traces in the upper atmosphere, ionization trails, chemical shifts, or even electromagnetic echoes that ripple across regions we have yet to detect? From mountaintops and space stations, researchers continue to listen, to watch, and to wait. Every sprite recorded is another page in an unfolding cosmic diary, one written not in words but in light and charge. The more we study them, the more they whisper of hidden architectures in the sky, networks of energy we are only beginning to understand. Sprites, in their brief and brilliant lives, may also carry lessons about interconnectedness. That a storm, deep in a continent, can reach out and touch the very edge of space. That a single bolt of lightning can echo upward in a luminous bloom that spans the boundaries of weather and space physics. They are events of extraordinary delicacy and scale, bridging realms both literal and symbolic. And yet, despite all our instruments and theories, sprites retain a kind of wildness, an unpredictability that resists full domestication by science. Even when we can model the electric fields, anticipate the charge distributions, and align the cameras just right, the sprite still arrives like a cosmic improvisation, sudden, asymmetric, often asymmetrical, painting the mesosphere with strokes of crimson plasma that no algorithm can fully predict. In recent years, scientists have begun layering radio frequency data on top of optical observations. These combined datasets reveal that sprites are not just visual spectacles but emit complex electromagnetic signatures, brief bursts of very low frequency, VLF, and extremely low frequency, ELF, radio waves that ripple through Earth's atmosphere and beyond. These signals travel vast distances, interacting with the ionosphere, bouncing between hemispheres, and potentially influencing the behavior of charged particles in the radiation belts. In this way, sprites are not just witnesses of energy exchange, they are participants in shaping the electromagnetic environment of our planet. Interestingly, some researchers have proposed that sprites may even have subtle effects on atmospheric chemistry. The intense electrical fields and localized ionization could, in theory, contribute to the formation or destruction of transient compounds like nitric oxide or ozone in the upper atmosphere. While these effects are likely to be minor compared to global processes, they serve as yet another example of how dynamic and alive our atmosphere truly is, even in layers once thought inert and passive. But sprites are not merely the concern of physicists and atmospheric chemists. Artists, poets, and skywatchers have begun to embrace them as symbols of something deeper, a reminder that even in the most storm-tossed environments, beauty can arise from chaos, structure from turbulence, and light from hidden tension. Capturing a sprite on film has become a kind of pilgrimage for astrophotographers, who must wait in darkness near thunderstorms, with specialized cameras trained toward the invisible, hoping for a millisecond of wonder. And sometimes, a single frame contains an entire cathedral of light, a cathedral built from arcs, streamers, and spires that reach upward like prayers from the earth to the stars. From a philosophical point of view, sprites blur boundaries. They are liminal beings, inhabiting the threshold between weather and space, matter and plasma, science and myth. Their behavior is rooted in quantum-level particle collisions and macro-scale electric fields, yet the form they take resembles the branches of a tree, the neurons of a mind, the roots of some inverted lightning-born forest growing down from the edge of the void. In that sense, sprites are metaphors for emergence, complex patterns arising from the interplay of simple laws, flashing into existence with elegance and then dissolving just as quickly. They also challenge our sensory expectations. Lightning roars and cracks across the sky, sprites do not. They are utterly silent to human ears. You may see one and hear nothing. And that silence makes them feel otherworldly, like a secret performed in another language. You must translate their meaning through instruments and physics, but you feel it through all. This quiet, momentary light connects us to an invisible realm of forces always at work just beyond perception. In that instant of red fire above the storm, the veil between Earth and space lifts. The planet breathes upward, and the heavens answer, not with thunder, but with flame. Physically, sprites emerge from the interplay of three critical systems: the thunderstorm below, the ionosphere above, and the mesospheric medium in between. When a large positive cloud-to-ground (CG) lightning discharge occurs, typically carrying currents of tens of kiloamperes, it removes a vast quantity of charge from the cloud top. This sudden shift in the electric field propagates upward at the speed of light, disturbing the quasi-electrostatic field between the thundercloud and the lower ionosphere. This altered electric field must meet a critical breakdown threshold in the mesosphere, where air density is sufficiently low to allow electrons to accelerate and multiply via avalanche ionization. The reduced neutral density at these altitudes increases the reduced electric field, E/N, a crucial parameter describing how efficiently electrons gain energy from the field relative to how often they collide with neutral molecules. At around 70 to 85 kilometers altitude, this ratio becomes optimal for triggering streamer formation, the slender plasma filaments that constitute the Sprite structure. Streamer theory, borrowed from high-voltage laboratory discharges, explains much of what we observe. Streamers are self-propagating plasma channels that advance via electron multiplication at their tips. In the Sprite context, upward and downward moving streamers form in clusters, sometimes with hundreds developing in parallel, leading to the familiar caret and column shapes seen in high-speed images. Laboratory simulations and fluid models show that these streamers propagate at velocities ranging from 10 to 10 cm/s and require background electric fields of several hundreds of volts per centimeter in the rarefied upper atmosphere. Interestingly, Sprite streamers are cold plasmas. Unlike lightning channels, where temperatures can reach 30,000 K, the electron temperature in Sprites may only be a few electron volts. 1 eV is almost equal to 11,600 K, and the ion and neutral temperatures remain close to ambient. The energy is concentrated in a small fraction of electrons, which gain sufficient velocity to ionize and excite atmospheric molecules, mostly nitrogen. The characteristic red light of Sprites comes from the first positive band system of molecular nitrogen, N21P, emitting strongly around 670 to 800 nanometers, with additional blue-violet contributions in the lower tendrils. Recent studies using time-resolved spectroscopy have resolved sub-millisecond transitions between excited states, confirming that Sprites evolved through a series of short-lived molecular interactions. The lifetime of the N21P state is on the order of nanoseconds, but because different streamer branches ignite sequentially, the whole event can last up to 10 to 20 milliseconds. Sophisticated modeling using the Poisson-Boltzmann equation, coupled with Monte Carlo simulations of electron transport, helps researchers understand the microphysical evolution of Sprites in 3 dimensions. Beyond the individual events, Sprites serve as real-time probes of the lower ionosphere, particularly the D region, around 60 to 90 kilometers, which is notoriously difficult to study due to its absorption of radio waves and inaccessibility to balloons and aircraft. When a Sprite occurs, it modifies the local electron density, creating transient ionospheric holes and perturbed regions detectable via VLF transmitter signals. This allows scientists to indirectly map the conductivity profile of the upper atmosphere and understand how space weather and solar activity modulate its behavior. Another scientific frontier involves the interaction between Sprites and gravity waves, oscillations in atmospheric density and pressure generated by storms, mountain ranges, or jet streams. Gravity waves can modulate the neutral background density in the mesosphere, influencing where and when Sprites can form. Some models even suggest that gravity waves can precondition regions of the sky, making them more or less receptive to electrical breakdown, effectively acting as invisible sculptors of Sprite geometry. In satellite data, Sprites often appear in concert with other transient luminous events, TLEs, such as blue jets, conical discharges erupting from thundercloud tops, and ELVs, rapidly expanding rings of optical emission produced by electromagnetic pulses, EMPs, that travel laterally at the speed of light. These TLEs occur at different altitudes, and together they form a vertical column of electrical phenomena that extends from the Earth's surface to the lower thermosphere, a system now understood as stratified electrical coupling. Through these studies, we've begun to appreciate that sprites are not isolated events but are embedded in a complex electrodynamic ecosystem linking ground-level meteorology to ionospheric chemistry and even magnetospheric dynamics. The global electric circuit, once a theoretical abstraction, now takes on physical clarity through the lens of sprites, revealing that every thunderstorm is not just local weather but a node in a planetary-scale electrical network. Laboratory experiments have become a powerful tool in advancing our understanding of sprite physics. Although we cannot recreate a full-scale sprite in the lab due to size and pressure differences, controlled experiments in low-pressure chambers using pulsed high-voltage systems have replicated the essential conditions of sprite streamer formation. These experiments often use needle plane or point plane electrode geometries to simulate the intense local electric fields that form at the streamer tip, and they employ nitrogen-oxygen mixtures at pressures equivalent to the mesosphere, 0.1 to 1 torr. One key result from laboratory analogs is the validation of streamer scaling laws. According to similarity principles, the behavior of streamers, velocity, diameter, branching frequency, scales with the reduced electric field, E/N, meaning we can study mesospheric discharges by appropriately scaling down pressure and adjusting the driving voltage. Experiments have confirmed that streamer heads in sprites propagate due to photoionization, where UV photons emitted from excited nitrogen molecules ahead of the streamer pre-ionize the medium, enabling continued growth in a low-density atmosphere. This non-local process is essential for sprite development, as it allows the plasma to advance into regions with insufficient background ionization. Computational models complement these experiments, using fluid, hybrid, and particle-in-cell (PIC) approaches to simulate sprite initiation and streamer propagation. Fluid models solve the coupled equations of motion for electrons and ions, along with Poisson's equation for electric potential, under mesospheric conditions. These models reveal instabilities at the streamer head, branching mechanisms, and charge deposition patterns. More advanced PIC simulations track individual particles, capturing kinetic effects such as electron energy distribution, secondary avalanches, and sheath dynamics. On a larger scale, global sprite climatology is now being mapped with satellite constellations such as NOAA's Quasar, ESA's ASIM aboard the ISS, and the Chinese LAS/GLM sensors, which can detect lightning flashes and their associated optical transients. These data sets have enabled the correlation of sprite occurrence with mesoscale convective systems, MCSs, showing that sprites are more common over continental land masses, particularly in mid-latitude regions during summer. The most prolific sprite-producing storms are usually quasi-linear convective systems, QLCS, with sustained, long-duration lightning activity and strong charge separation. From these global datasets, researchers have derived statistical properties of sprites, their typical delay after apparent lightning stroke, 10-50 ms, altitude range, 50 to 90 kilometers, horizontal span, 10 to 50 kilometers, and optical intensity, up to several megarayleigh. A megarayleigh is an astronomical unit of brightness, and a sprite can briefly outshine the night sky background by orders of magnitude, though not enough to be easily seen without equipment. The connection between sprites and the Schumann resonances, natural resonant frequencies of Earth's electromagnetic cavity, about 7.8, 14, and 20 Hz, is another frontier of study. Some researchers propose that large-scale TLE activity modulates global resonance amplitudes, subtly altering the electromagnetic environment for days or weeks after large thunderstorm outbreaks. This connects sprites to broader questions in geophysics, such as the coupling of the lithosphere, atmosphere, ionosphere system and the potential for electromagnetic precursors to seismic events. There's even emerging interest in the biological implications of sprites and related phenomena. Though far above commercial flight altitudes, the electromagnetic pulses associated with sprites and TLEs could affect the local radiation environment in the mesosphere and lower thermosphere. Some theoretical work suggests that cosmic ray particles interacting with sprite-related fields may produce runaway electron avalanches or high-energy X-ray and gamma-ray emissions, part of what are now called terrestrial gamma-ray flashes, TGFs. These TGFs, detected by missions like NASA's Fermi Gamma-Ray Space Telescope, suggest that thunderstorms and associated phenomena like sprites may be among the most energetic natural particle accelerators on Earth. This positions sprites not only as spectacular optical displays, but also as critical agents in high-energy atmospheric physics. Their study overlaps with astrophysics, radiation physics, and even quantum electrodynamics. The Earth, it turns out, is not just a passive receiver of cosmic energy, it generates bursts of relativistic particles in its own sky, using thunderstorms as launch pads and sprites as signals. Planetary analogues of sprites open a new and thrilling dimension in the study of atmospheric electricity. If gigantic red sprites are the Earth's way of discharging extreme electrical tension between tropospheric storms and the ionosphere, then it is plausible that similar mechanisms may operate on other planets, especially those with thick atmospheres, convective cloud systems, and strong magnetic fields. Jupiter, for example, has the most powerful thunderstorms in the solar system. Observations by the Juno spacecraft have confirmed lightning at depths far below the ammonia cloud decks, with bolts potentially thousands of times more energetic than those on Earth. Juno's ultraviolet spectrometer has recorded flashes of light at altitudes far above these storm regions, flashes that resemble the hallmarks of transient luminous events, TLEs. These include rapid, upward propagating discharges with a spectral signature compatible with excited hydrogen, suggesting the presence of Jovian analogues to sprites and elves. Unlike Earth, where sprites arise primarily from molecular nitrogen emissions, Jupiter's upper atmosphere is dominated by hydrogen and helium, so any Jovian sprite would likely appear as a blue or ultraviolet flash due to the different emission spectra of atomic and molecular hydrogen. This offers a new challenge: how to adapt Earth-based detection techniques, designed around nitrogen red emissions, to find sprite-like events on gas giants with different chemistries and atmospheric pressures. Saturn, too, exhibits massive electrical activity. The Cassini mission detected persistent lightning storms in its equatorial belts, with flashes powerful enough to be seen from orbit for weeks at a time. While direct evidence for sprites on Saturn remains elusive, models suggest that the enormous vertical extent of its atmosphere and ionosphere could allow for massive high-altitude discharges, possibly dwarfing Earth sprites in size and energy. The ionospheric boundary on Saturn lies far above its cloud tops, offering an immense electric field potential and a large spark gap in which TLEs might form. Venus presents a different, more enigmatic case. Though its lightning is not yet definitively confirmed, electromagnetic anomalies recorded by Soviet Venera and later by ESA's Venus Express suggest possible thunderstorm activity within its thick sulfuric acid cloud layers. If sprites do exist on Venus, they would need to propagate through an atmosphere dominated by CO2, with a dense and thermally layered stratification. Modeling shows that such discharges might produce a greenish or yellowish light due to emissions from CO2 and atomic oxygen, although the high background brightness of the Venusian atmosphere would make detection extremely difficult. Beyond our solar system, the study of sprites may even intersect with exoplanet research. Brown dwarfs, objects between the mass of a planet and a star, show signs of powerful atmospheric storms and radio emissions that may be consistent with lightning and TLE-like phenomena. If sprites exist there, they may occur in atmospheres composed of exotic molecules such as silicates, metals, or ammonia, emitting light in entirely unfamiliar spectral regions. Detecting such events could become a new method for remote sensing of alien atmospheres. Back on Earth, One of the most fascinating links between sprites and high-energy physics comes from their association with relativistic runaway electron avalanches, RAs. Under strong electric fields in thunderstorms, electrons can be accelerated to near light speed if they avoid enough collisions. These high-energy electrons can produce X-rays and gamma rays as they collide with air molecules. This is the mechanism behind terrestrial gamma-ray flashes, TGFs, which were first discovered by NASA's BATS instrument in the 1990s. Sprites appear to correlate with TGFs in certain cases. Some models propose that the electric fields above thunderstorms, especially those that generate sprites, may serve as secondary acceleration zones for upward-moving relativistic particles. In this sense, sprites might serve as beacons not just of electrical breakdown but of high-energy particle acceleration, a role previously thought exclusive to astrophysical environments like pulsars and black hole jets. There is even speculation that such particle showers could have influenced Earth's atmospheric chemistry over geological timescales. During periods of intense storm activity or geomagnetic variation, the increased flux of gamma rays and secondary particles from thunderstorm-induced discharges could alter the production rates of nitrates and contribute to transient climatic effects. Although speculative, this idea opens a new interdisciplinary frontier connecting atmospheric electricity, climate science, and geochemistry. Sprites, therefore, sit at the nexus of many disciplines: electrodynamics, atmospheric science, quantum physics, astrophysics, and even planetary science. They are natural laboratories for studying breakdown processes in rarefied gases, mechanisms of plasma propagation, and energy transfer across layers of the atmosphere and beyond. They remind us that the boundary between Earth and space is not a wall, but a membrane, flexible, dynamic, and alive with processes we are only beginning to observe. At the quantum scale, Sprite streamers represent an exquisite example of how macroscopic electrical structures emerge from microscopic particle dynamics governed by probabilistic collisions, field interactions, and quantum excitation states. Though sprites stretch tens of kilometers in height, the processes driving them originate at the scale of nanometers, within the energy exchanges of individual electrons and molecules in a thin, partially ionized upper atmosphere. In a sprite streamer, free electrons, seeded by cosmic rays, earlier lightning pulses, or photoionization, are accelerated by intense local electric fields. As they accelerate, they collide with neutral molecules, primarily N2 and O2. If the electric field exceeds the breakdown field, approximately 120 V/m at 70-80 km altitude, electrons can gain enough energy between collisions to ionize these molecules, releasing more electrons. This cascading chain reaction, electron impact ionization, is the foundation of avalanche breakdown, which underpins the streamer mechanism. But this is only part of the story. During these high-energy collisions, electrons also excite the rotational, vibrational, and electronic states of nitrogen molecules. These excited molecules then decay, emitting photons across the visible and near-infrared spectrum. The specific red hue of sprites is largely attributed to transitions in the first positive band system of molecular nitrogen, N2b superscript 3 pi_G A superscript 3 sigma_U, peaking around 670 to 800 nanometers. These transitions are quantum mechanical in nature and are governed by selection rules, oscillator strengths, and radiative lifetimes on the order of nanoseconds. Spectroscopic studies using high-speed instruments have captured the time evolution of these emissions, revealing how different excited states contribute to different parts of the sprite structure. For example, the tendrils in the lower portion of a sprite often show stronger emissions from the second positive band, C superscript 3 pi_U B superscript 3 pi_G, which appears more bluish and indicates higher electron energy densities. These fine-scale observations allow scientists to infer the reduced electric field, E/N, electron energy distribution functions, EEDFs, and the mean energy of the ionization-producing electrons, all essential parameters in plasma physics. In the streamer head, the narrow tip of the propagating plasma channel, the electric field can be amplified to 10 times the ambient value due to local space charge effects. Here, nonlinear electron kinetics dominate. The energy spectrum of electrons becomes highly skewed, allowing for rare but extremely energetic collisions that can produce ultraviolet photons, initiate photoionization far ahead of the streamer, and even generate low-yield Bremsstrahlung X-rays. These localized electron clouds also serve as sources of Cherenkov radiation, a phenomenon more often associated with particle detectors and nuclear reactors. Moreover, in high-altitude conditions, streamer propagation becomes increasingly influenced by non-local electron transport. Unlike in dense gases where collisions rapidly thermalize electrons, in the mesosphere, the mean free path can exceed several centimeters. This allows electrons to be guided by spatially extended electric fields, resulting in more complex streamer morphologies, spirals, forks, or simultaneous upward and downward growth. Such structures have been modeled using Boltzmann solvers and kinetic Monte Carlo simulations, bridging quantum-scale particle motion with observable mesoscale patterns. Interestingly, the Sprites interaction with the ionosphere can generate Whistler mode waves and Schumann resonances, extremely low-frequency (ELF) electromagnetic waves that propagate globally through the Earth ionosphere waveguide. These signals, often detectable halfway across the globe, carry the electromagnetic fingerprint of a single Sprite-producing lightning event. By analyzing the timing, frequency content, and amplitude of these signals, scientists can back-calculate the characteristics of the lightning discharge and the corresponding Sprite. This global detectability has enormous implications. It means that Sprites, though localized, participate in the dynamics of space weather, the study of how solar, atmospheric, and magnetospheric processes affect near-Earth space. For instance, during geomagnetic storms, variations in the Earth's magnetic field can alter the conductivity of the ionosphere, affecting Sprite formation thresholds and altering the shape of the global electric circuit. In this way, Sprites serve as indirect indicators of solar activity's terrestrial consequences. Some theories even suggest that the cumulative electromagnetic and particle output from Sprite-producing storms could influence the distribution of trapped electrons in the Van Allen radiation belts. These belts, composed of energetic charged particles held in place by Earth's magnetic field, are sensitive to disturbances in the ionosphere. If Sprites modulate the density of the D region, they may affect the reflection and propagation of plasmaspheric His and other wave modes that scatter belt electrons into the atmosphere. As this field matures, a unified theory of electrodynamic coupling is emerging, one that links the microphysics of streamer discharges with global circuits, planetary magnetospheres, and even cosmic ray modulation. Sprites, once dismissed as rare curiosities, are now seen as dynamic agents within a complex, multi-scale electrosphere, a region where chemistry, electricity, and plasma turbulence co-evolve in delicate balance. Detection and classification of Sprites have undergone a revolution in recent decades, moving from serendipitous observations to precise, multi-instrument campaigns that combine optical, radio, and electromagnetic data from both ground-based and space-based platforms. This coordinated strategy allows researchers to not only capture Sprites visually but also to triangulate their location, determine their altitude, classify their morphology, and infer the physical conditions that triggered them. From the ground, high-speed, low-light video cameras, often equipped with image intensifiers and narrowband filters, are mounted at observatories or mobile storm-chasing platforms. These systems typically operate at 10,000 to 100,000 frames per second, allowing them to resolve the temporal evolution of Sprite streamers and their branching patterns. By using synchronized camera arrays separated by known distances, researchers can apply stereoscopic techniques to calculate the 3D geometry of a Sprite with kilometer-level precision. In tandem, electromagnetic sensors detect the extremely low frequency, ELF, and very low frequency, VLF, waves produced by both the initiating lightning and the sprite itself. VLF receivers can be located hundreds to thousands of kilometers away from the source and still detect the signal due to its propagation within the Earth ionosphere waveguide. Time of arrival and direction-finding methods allow scientists to pinpoint the lightning stroke responsible for the sprite, while spectral analysis of the ELF/VLF waveforms provides information about current intensity and discharge polarity. At higher altitudes, satellite-based instruments like ASIM, Atmosphere, Space Interactions Monitor, and Tyrannies, tool for the analysis of radiations from lightnings and sprites, were designed to capture sprites from orbit. These instruments combine optical photometers, X-ray/gamma-ray detectors, and electric field antennas to study transient luminous events, TLEs, in their full electromagnetic context. Orbiting above thunderstorms, they offer a unique top-down perspective, crucial for studying the large-scale structure of sprite clusters and their relation to the underlying convective systems. With these tools, scientists have identified several distinct sprite morphologies, each reflecting subtle differences in atmospheric conditions, electric field configurations, and initiation mechanisms. Column sprites appear as narrow vertical channels extending tens of kilometers downward. They typically form first and mark the primary path of the downward propagating streamer front. Caret sprites are more complex, exhibiting a wide, bright top that narrows into multiple downward streamers. These are often associated with stronger electric fields and longer-lasting discharges. Jellyfish sprites are among the rarest and most magnificent, displaying wide, glowing heads with multiple tendrils that span over 40 kilometers horizontally. These usually occur during large mesoscale convective systems and may reflect enhanced ionospheric conductivity gradients. Angel sprites, a recently proposed category, appear bilaterally symmetrical with upward and downward streamers and may be linked to internal gravity waves shaping the mesospheric density field. These shapes are not merely aesthetic variations, they encode physical information. For example, the width of the upper halo can be used to estimate the vertical profile of ionospheric conductivity. The number and brightness of tendrils can indicate the magnitude of the parent lightning current. And the presence of upward streamers suggests complex charge motion near the ionosphere, possibly a sign of bidirectional discharge. Climatologically, sprites are more likely to occur over large land masses with intense summer thunderstorm activity. The central United States, South America's Gran Chaco region, the African Sahel, and parts of Southeast Asia are among the global hotspots. Seasonal maps show a strong correlation with the Intertropical Convergence Zone, ITCZ, and regions of high convective available potential energy, CAPE, suggesting that sprite activity is tightly coupled to deep convective weather systems. Statistical studies of sprite occurrence reveal several trends. Sprites are most commonly triggered by positive CG lightning, which accounts for less than 10% of all lightning strokes but carries a higher charge moment change. The likelihood of sprite production increases significantly when the charge moment change, CMC, exceeds 500 to 1000 c/km, a parameter representing the product of transferred charge and its vertical displacement. Sprites tend to cluster spatially and temporally during mesoscale convective system, MCS, life cycles, often forming near the rear flank stratiform region where intense positive lightning occurs. The occurrence of sprites increases during nocturnal hours, especially in the local post-midnight period. This is likely due to enhanced ionospheric transparency and reduced background light. Moreover, long-term sprite monitoring campaigns are beginning to uncover multi-year and possibly decadal trends that may be linked to solar cycles, ENSO, El Niño, southern oscillation, phases, and global temperature anomalies. If confirmed, this would make sprites valuable proxies for understanding deeper climate, electrodynamic coupling on Earth. Sprites, though brief, serve as fingerprints of extreme energy redistribution in the atmosphere. They form part of a dynamic cascade: thunderstorm lightning, electromagnetic pulse, mesospheric breakdown, chemical alteration, global circuit modulation. Every sprite is a localized event, yet a window into planetary scale systems. The connection between sprites and cosmic rays opens a compelling chapter in the interplay between Earth's atmosphere and the broader cosmos. High-energy cosmic rays, mostly protons and atomic nuclei from distant supernovae, quasars, or possibly more exotic extragalactic sources, continuously rain down on Earth, colliding with molecules in the upper atmosphere and creating showers of secondary particles, muons, pions, electrons, and gamma photons. These interactions are not just a passive background, they can actively seed the electrical conditions necessary for sprites. In the mesosphere, where sprites bloom, the air is tenuous and partially ionized, and local conductivity is highly sensitive to incoming ionization sources. When cosmic rays penetrate this region, they can deposit clusters of free electrons, so-called ionization trails, that lower the threshold for electrical breakdown. In this way, a sprite-producing electric field may succeed in forming a discharge only because a cosmic ray happened to pass through a critical volume microseconds earlier. Some models suggest that relativistic runaway electron avalanches, RRAs, triggered by both thunderstorm fields and cosmic ray seed electrons, may help launch sprites under borderline conditions. RRAs occur when ambient electric fields are strong enough to accelerate electrons faster than they lose energy through collisions, allowing a single high-energy electron to initiate a cascading particle storm. If such avalanches extend into the mesosphere, they could act as invisible fingers igniting the sprite's visible plasma. Research using ground-based cosmic ray detectors and synchronized sprite observation arrays has found statistical correlations between increased cosmic ray flux and higher sprite activity, particularly during periods of low geomagnetic shielding or solar minimum, when cosmic rays penetrate more deeply into the atmosphere. These findings suggest that sprites may, in some cases, act as magnifiers of the cosmos, turning invisible particles from distant galaxies into luminous events visible from Earth. This raises tantalizing questions about how sprites may influence, or even define, biospheric boundaries. The mesosphere and lower ionosphere form the upper envelope of Earth's life-supporting shell, separating living organisms from the high-energy radiation of space. While sprites are too rare and brief to directly affect life on the ground, their associated processes, ionization, electromagnetic pulses, chemical reactions, could have implications for airborne biology, including high-altitude microbial dispersal, viral nucleic acid stability, or the survival of extremophiles in the stratosphere and beyond. Some scientists have speculated that in Earth's early atmosphere, before the development of a thick ozone layer, sprite-like discharges may have been more frequent, more energetic, and more chemically influential. The mesosphere at that time may have been a kind of electrochemical crucible, where ultraviolet radiation, volcanic emissions, and high-energy discharges combined to generate complex organic molecules. In laboratory experiments that simulate prebiotic conditions, high-voltage plasma discharges in methane, ammonia, CO2, N2 mixtures, at pressures corresponding to ancient mesospheric levels, can synthesize amino acids, nucleobases, and other life precursor molecules. If natural sprites acted similarly, they may have contributed to the prebiotic synthesis of biomolecules long before the emergence of cellular life. This makes sprites not merely electrical curiosities but potential agents in life's origin story. On other worlds, this connection grows even more profound. Imagine an early Earth-like exoplanet with an active thunderstorm cycle, a weak magnetic field, and abundant atmospheric nitrogen. If such a planet also experiences frequent cosmic ray bombardment, especially from a nearby supernova or active galactic nucleus, its mesosphere could be a factory of plasma discharges and photochemistry. Sprites, alien yet familiar, might ignite there too, building molecular complexity in high-altitude realms beyond reach, offering a plausible path toward prebiotic chemistry in the absence of surface oceans or UV-irradiated ponds. From this perspective, sprites are more than weather, they are astrobiological phenomena, emergent structures that encode the interaction of planetary electricity, cosmic energy, and chemical potential. They represent how the universe, through storm and silence, sculpts complexity in the skies. Expanding into the realm of technological potential, sprites are increasingly recognized not only as objects of study, but as tools, natural sensors that can reveal hidden features of Earth's atmosphere, its ionospheric structure, and even incoming cosmic disturbances. These high-altitude discharges act like massive, transient electrodes, briefly illuminating and perturbing otherwise inaccessible regions of the atmosphere. In this way, sprites become diagnostic instruments, not constructed by humans, but sculpted by nature. Because sprites occur in the mesosphere and lower ionosphere, they provide real-time information about a part of the atmosphere that is notoriously difficult to study. Balloons cannot reach it, aircraft cannot fly there, and satellites often orbit too high to resolve fine-scale phenomena. But when a sprite occurs, it acts as a probe, disturbing the electron density and generating waves that ripple across surrounding altitudes. Scientists have learned to read these ripples, just as a seismologist reads tremors from distant earthquakes. For instance, VLF and ELF radio waves, generated or modulated by sprites, are reflected by the D region of the ionosphere. By measuring how these waves bounce and change, researchers can reconstruct the local electron density, temperature, and even chemical composition of the upper atmosphere. This technique is especially useful during solar flares, geomagnetic storms, or high-energy particle events, when the ionosphere is rapidly and unpredictably disturbed. Sprites can also serve as early indicators of space weather. Just as a lightning flash might foreshadow a growing storm, a spike in sprite activity, particularly in conjunction with blue jets or elves, may signal the arrival of magnetospheric disturbances, changes in global electric circuit behavior, or increased cosmic ray flux. By monitoring global sprite activity in near real time, space weather forecasters could gain new tools to anticipate changes in ionospheric reflectivity, satellite drag, or even ground-based technological risk. Another frontier of sprite-based diagnostics involves atmospheric gravity waves. These slow, oscillating waves are generated by imbalances in air masses, often caused by mountains, storms, or jet streams, and they propagate vertically, modulating air density in the upper atmosphere. Sprites appear to ride these invisible waves, sometimes clustering in specific regions where the background atmosphere has been preconditioned by density perturbations. By mapping sprite occurrence in relation to known gravity wave activity, researchers can indirectly study the global propagation of these waves, which play key roles in weather and climate systems. Sprites might even help us monitor anthropogenic influences on the atmosphere. As the climate warms and thunderstorms become more intense, the frequency and strength of lightning increases, particularly positive CG strikes, which are the main triggers for sprites. A statistically significant increase in sprite frequency over time could therefore act as a kind of planetary, vital sign, signaling shifts in global atmospheric energy balance and convective dynamics. On the technological horizon, there is growing interest in using cube satellites, CubeSats, to monitor sprites from low Earth orbit. These small, inexpensive platforms can carry photometers, high-speed imagers, and electromagnetic sensors, allowing a distributed network to capture sprite activity across the globe with unprecedented coverage. When coupled with ground-based camera arrays and VLF receiver networks, such a system could provide a global sprite tomography grid, a new way of mapping the dynamics of Earth's upper atmosphere in 4D, space, time, energy, and chemistry. Beyond Earth, sprites could also serve as probes of other planetary environments. Imagine orbiters around Jupiter or Venus equipped with sensitive light detectors and ELF antennas, tuned to detect transient optical and electromagnetic flashes in alien skies. A single confirmed sprite on another world would validate decades of theory and open a new channel of planetary diagnostics. Even without direct imagery, the spectral signatures of such discharges, brief emissions at known wavelengths, could act as fingerprints of atmospheric composition, pressure, or conductivity. In this way, sprites become not just subjects of awe or curiosity, but functional instruments in our expanding toolbox of space and atmospheric science. They offer a unique combination of vertical reach, electromagnetic breadth, and chemical impact, making them, arguably, one of the most powerful natural laboratories we have for studying high-altitude physics. Would you like the next section to explore future missions and AI-powered sprite detection, or venture into speculative theoretical physics, sprites as analogs for plasma processes in other astrophysical systems, such as jets from black holes or stellar coronae? And so, in the fleeting glow of a gigantic red sprite, we glimpse a vast and subtle dialogue, between earth and sky, matter and energy, chaos and form. These ghostly flames, born from storms but reaching toward space, are more than electrical ephemera. They are signatures of the planet's inner charge, markers of invisible architectures, and emissaries from a realm where weather dissolves into plasma and physics becomes poetry. Sprites remind us that even in the most ephemeral flashes, deep structures reveal themselves. They are born in silence, above the thunder, yet speak of forces that ripple across the globe and beyond. They record the breath of the planet, the influence of the cosmos, and the restless balance of energy that animates the atmosphere. To study them is to enter a domain where disciplines converge: electrodynamics, quantum mechanics, climate science, planetary exploration. To witness them is to realize that the sky is not empty, but alive. And to understand them is to know that the boundary between Earth and the universe is not fixed, but fluid, charged, reactive, luminous. Sprites are not just lightning's silent cousins. They are messengers. They are instruments. They are echoes of something greater. Fleeting, yet eternal in their meaning. A red signature on the dark canvas of the cosmos. NGC 2685, also known as the Helix Galaxy, is one of the most peculiar and captivating structures in the nearby universe. Unlike typical spiral or elliptical galaxies, it defies conventional classification, presenting a bizarre, twisted configuration that astronomers describe as a polar ring galaxy. This rare form reveals two distinct components: a central lenticular or elliptical body, surrounded by a nearly perpendicular ring of gas, stars, and dust. The result is a gravitational ballet frozen in time, a warped, multidimensional sculpture that seems to rotate along two axes simultaneously. Its morphology suggests a violent past. The outer ring, rich in neutral hydrogen and young stars, likely formed from a collision or accretion event, where NGC 2685 cannibalized a smaller companion galaxy. Instead of settling into the plane of the host galaxy, the captured material stabilized into an orbit nearly orthogonal to the central structure, leading to the galaxy's current twisted shape. Such a configuration is gravitationally stable over cosmic timescales, defying expectations of rapid decay or realignment, which highlights the remarkable complexity and resilience of galactic dynamics. NGC 2685 is located approximately 42 million light-years away in the constellation Ursa Major. Despite its relatively close proximity, its true structure was obscured for decades due to our earthbound, edge-on view. Early observers believed it to be a simple elliptical galaxy with some internal dust lanes. Only with the advent of multi-wavelength observations and detailed kinematic studies did its polar ring nature become apparent. These insights were further enhanced by radio observations tracing the extended hydrogen envelope, revealing a disk in near-perfect perpendicular rotation to the central axis. The coexistence of two stellar populations rotating at different angles is a unique laboratory for understanding galaxy evolution and angular momentum transfer. While the inner component consists mostly of older stars and displays little recent star formation, the outer ring hosts regions of active star birth, indicating a dynamic interplay between stability and disruption. This duality allows astronomers to study how gas behaves when accreted in misaligned orbits, providing insights into how galaxies grow through minor mergers and cosmic infall. Unlike many more luminous or well-known galaxies, NGC 2685 emits relatively little in the infrared and ultraviolet, making it a subtle but significant player in the larger narrative of galactic transformation. The absence of strong active galactic nucleus activity also suggests that its central black hole, if present, remains dormant or underfed. This allows astronomers to examine the gravitational interactions without the confounding influence of energetic outflows or jets. Some simulations suggest that galaxies like NGC 2685 might represent a transitional phase, an intermediate step in the hierarchical assembly of larger galaxies. Over billions of years, the outer ring may dissipate, merge, or become fully integrated into the host body, erasing the striking polar features and leaving behind only faint relics in stellar velocity maps. Observing such a structure today is akin to catching a rare snapshot of a fleeting cosmic configuration, an architectural trace of collision and stability coexisting in precarious balance. Its isolation in the sky further deepens the enigma. NGC 2685 doesn't reside in a dense galactic cluster, reducing the likelihood that tidal forces alone shaped its form. This makes the accretion theory even more compelling, possibly involving a long-dead dwarf galaxy whose remains now trace a luminous halo in the polar plane. The stellar populations within the ring differ chemically from those of the central bulge, further supporting a multi-origin scenario. The question of longevity remains central to its study. The polar ring must balance against gravitational torques and precession forces, and yet NGC 2685 has maintained its integrity for hundreds of millions of years. Such endurance hints at a finely tuned dynamical equilibrium, where mass distribution, rotation, and orbital mechanics synchronize to prevent collapse. It may serve as a reference model for understanding galactic warps, misaligned accretion disks, and even the formation of polar disks in early-type galaxies throughout the universe. If the galaxy had a voice, it might speak of dualities, of being torn between two frames of rotation, two histories, two fates. The core remains stoic and motionless by cosmic standards, while the ring circles with a youthful defiance, tracing arcs of light across an ancient sky. The light we receive from NGC 2685 carries the signatures of both calmness and conflict. Spectroscopic analysis reveals stark contrasts between the chemical composition and stellar velocities in the polar ring and the central bulge. While the nucleus shows signs of population aging and metallicity enrichment typical of lenticular galaxies, the polar ring is abundant in younger, metal-poor stars and ionized gas, echoing a more turbulent and recent origin. This juxtaposition creates a living archive of astrophysical time, where one galaxy contains relics of two epochs, layered not chronologically, but spatially. Rotation curves derived from hydrogen line measurements unveil a beautifully choreographed contradiction, two rotating systems intersecting through gravity, yet remaining in stable alignment. The ring doesn't merely orbit, it precesses subtly, hinting at the slow influence of torques and mass asymmetries over eons. Such measurements challenge older models of galactic evolution that favored symmetry and simplicity, pushing astronomers to account for multi-spin configurations in both isolated and group environments. In terms of luminosity, NGC 2685 is modest. It doesn't blaze with the brilliance of active galactic nuclei nor flood the sky with the starburst frenzy seen in merging systems. Its beauty lies instead in its contradiction, subtle, understated complexity hidden within an apparently ordinary shell. Optical imaging reveals the wispy outlines of the polar ring wrapping like a luminous helix, while deeper exposures show diffuse arcs extending beyond the visible ring, suggesting that the structure may be even larger and older than first thought. The rarity of polar ring galaxies like NGC 2685 cannot be overstated. They represent less than 0.5% of all observed galaxies, and each known specimen offers a distinct configuration. This uniqueness makes NGC 2685 not just an oddity, but a critical piece of the broader puzzle of cosmic structure formation. By studying such systems, astronomers can reverse engineer the processes of angular momentum transfer, gas accretion, and dynamical stability. It also opens questions about dark matter distribution, whether the halo around NGC 2685 is spherical, triaxial, or flattened, and how it influences the orbital planes of such dramatically misaligned components. Advanced simulations aiming to recreate galaxies like NGC 2685 require fine-tuning and high-resolution modeling to match observed features. These models must account for not just the gravitational collapse and merger history, but also gas cooling, star formation feedback, and long-term orbital evolution. Despite technological advances, no simulation has yet perfectly recreated the full complexity and longevity of NGC 2685 structure, suggesting that nature still guards some of its secrets behind layers of gravitational subtlety. On a philosophical level, NGC 2685 offers a metaphor for resilience and multiplicity. It is a system that defies linear history, instead embracing contradiction as structure. It teaches that galaxies, like civilizations, are not always formed by isolated growth but by the layering of interactions, collisions, and reconnections. One orbit speaks of quiet continuity, the other, of a cataclysmic past now tamed into harmony. The galaxy becomes a cosmic palimpsest, its older structure overwritten not with erasure, but with luminous revision. Its study has implications beyond aesthetics or classification. Polar ring systems may help refine our understanding of halo mass distributions, galactic shape inference, and even the processes governing star formation under angular shear. The stars in the ring feel both the pull of the central mass and the collective torque of their neighbors, creating star-forming conditions unlike those in typical spiral arms. Such dynamics may mirror conditions in early galaxies of the universe, where gas often fell in chaotically from the cosmic web at skewed angles, forming misaligned disks and rings. NGC 2685 also provides a valuable calibration tool for testing observational techniques. Because it contains two orthogonal rotating systems, astronomers can probe projection effects, three-dimensional dynamics, and velocity field modeling. It's a natural testbed for verifying the accuracy of spectral decomposition, spatially resolved kinematics, and dark matter mapping. In this sense, it is both a celestial phenomenon and a scientific instrument shaped by the universe itself. As telescopes become more advanced, the insights gleaned from NGC 2685 only deepen. Instruments like the Very Large Array and the Hubble Space Telescope have peeled back layers of its structure, revealing not only the shape of its gaseous and stellar components but also the faint filaments and arcs that may extend far beyond the visible ring. Future observations with high-resolution integral field units and space-based observatories like the James Webb Space Telescope may uncover even subtler details, hidden star-forming knots, faint tidal streams, or traces of the original companion galaxy long since absorbed. What is particularly intriguing is how the polar ring interacts with the interstellar medium. The compression of gas along the ring's orbit appears to foster the formation of stellar clusters in periodic bursts, much like beads strung along a wire. These clusters can then be studied to determine their age gradients, metallicity variations, and kinematic histories, offering a detailed timeline of how the ring evolved after the accretion event. Each stellar generation becomes a timestamp, marking epochs in a slowly turning wheel of galactic transformation. The polar ring may also offer indirect evidence about the dark matter halo enveloping the galaxy. If the dark matter distribution were purely spherical, the ring's long-term stability would be easier to explain. However, observations suggest that triaxial or flattened halos might be more realistic, and the way the ring precesses, or doesn't, can help constrain these models. NGC 2685, therefore, becomes a natural laboratory not just for visible matter, but for probing the invisible architecture of gravity that shapes galaxies on large scales. From a cosmological perspective, galaxies like NGC 2685 are fossil records of a more chaotic, merger-driven universe. In today's relatively sedate cosmic age, such dramatic accretion events are rare. But billions of years ago, when the universe was denser and more interactive, these events were more common, leaving behind relics like polar rings, warped disks, and extended tidal tails. Studying NGC 2685 allows astronomers to infer not just its past, but the conditions of the early universe that made such structures possible. Even now, there may be subtle internal shifts underway. Low-level torques, magnetic influences, and internal instabilities may slowly warp the ring, pull it inward, or cause its star-forming regions to migrate. Over the next few billion years, this elegant duality could dissolve into a more homogeneous form, blending into the surrounding stellar population and losing its distinctive geometry. Like all cosmic structures, NGC 2685 is temporary, an intricate configuration frozen in a moment that we, by chance, are alive to witness. It's easy to overlook galaxies like this amid the grandeur of quasars, colliding clusters, and supernovae. But NGC 2685 is a quiet anomaly, a whisper in the cosmic chorus, telling a different story. It doesn't shout with brightness, but instead invites those who look deeper to find meaning in asymmetry and balance. It reminds us that the universe is not always elegant in the classical sense, but often in the way that chaos can evolve into structure, and that even in disorder, there is order waiting to be discovered. The Helix Galaxy, then, is more than a name. It evokes the spiral not of simple rotation, but of entwined histories, motion wrapped around motion, time coiled through space. It carries the legacy of encounters long past, yet still visible in the present. Each orbit, each ring of stars, each trace of cold hydrogen is a sentence in a galactic memoir written across millions of light-years. And in reading it, we uncover not only the fate of a single galaxy but echoes of how galaxies live, merge, remember, and change. In the delicate dance of NGC 2685, one finds echoes of cosmic memory, an enduring imprint of a past event so transformative that it redefined the very geometry of the galaxy. This is not merely a collision frozen in aftermath, but a living structure, still responding to the gravitational consequences of that ancient interaction. Every precessing star in the ring, every cloud of hydrogen tracing a polar arc, behaves as if it remembers the infall, the absorption, and the gravitational rebalancing that followed. The ring itself is not a perfect, uniform structure, it is subtly warped, slightly offset, and rich with asymmetries. These imperfections are not flaws, but fingerprints, evidence of the initial conditions of the captured material and the influence of the galaxy's mass distribution over time. Unlike spiral arms that wind neatly within the galactic plane, the polar ring slices diagonally through space, carving its own dynamic path as it weaves a halo of light and motion around the host body. It behaves as both a companion and a contradiction, gravitationally bound yet geometrically separate. The stellar populations within the ring span a range of ages, suggesting episodic waves of star formation triggered by internal compressions or weak interactions with the host galaxy's gravitational potential. These periodic surges of activity may be akin to galactic breathing: inhale as gas flows inward and condenses, exhale as new stars ignite and feed back energy into the surrounding medium. This cyclical rhythm adds another layer of complexity, transforming the ring from a passive remnant into an active stellar nursery, continuously reshaping itself across millions of years. The core of NGC 2685 remains enigmatic. Though lacking the violent outbursts of active galactic nuclei, its calm is deceptive. Buried within the central bulge is likely a supermassive black hole, modest by Quasar standards, but still millions of times the mass of the Sun. Its silence may be temporary. Should new material eventually spiral inward from the polar ring, it could awaken with a new cycle of activity. In this way, the past, present, and future of the galaxy remain connected by gravitational bridges and slow drifts of matter across cosmic time. NGC 2685 challenges the very definitions we use to categorize galaxies. Is it a spiral? An elliptical? A ring system? In truth, it resists singular identity. It exists in a liminal state, between types, between histories. Its form is neither purely accidental nor entirely predictable, it is the outcome of a unique set of initial conditions amplified over eons. For this reason, astronomers often see it as a case study in galactic identity, how shape and structure are shaped by history, interaction, and persistence. As our understanding of the universe expands, so too does our appreciation for galaxies like NGC 2685. They remind us that the cosmos is not defined solely by its grand explosions or the luminous beacons of quasars, but also by its quiet complexity, its ability to maintain structure amid chaos, to balance competing motions, to evolve into something stable yet strange. They reveal that harmony in the universe is not the absence of contradiction, but its resolution. In its geometry, we read the language of dynamics, in its light, the signatures of transformation. It is a galaxy of paradoxes, stable yet warped, silent yet evolving, symmetrical yet asymmetric, solitary yet shaped by encounter. It invites us to look again at what seems simple, to reconsider what we think we know, and to wonder at the hidden choreography of matter and motion in deep space. NGC 2685 orbits not just in its own frame, but within our collective scientific imagination, as a symbol of what galaxies can become when disturbed, and how beauty can emerge from disarray. It is a cosmic reminder that even the most unlikely configurations can endure, balance, and thrive in the grand architecture of the universe. NGC 2685 is not merely an astronomical curiosity, it is a profoundly instructive and multidimensional structure that embodies some of the most intricate principles of galactic dynamics, angular momentum conservation, and the long-term evolution of gravitational systems. Its most defining feature, a nearly perpendicular polar ring orbiting an older, lenticular host galaxy, is not simply a visual anomaly but a direct consequence of complex astrophysical processes unfolding over cosmic timescales. The current structure of NGC 2685 is thought to be the result of a past accretion event, most likely involving the capture and gradual assimilation of a gas-rich dwarf galaxy. Rather than merging completely and uniformly with the central body, the infalling material settled into a stable polar orbit, defying intuitive expectations that such material should quickly align with the galaxy's equatorial plane due to torques. This remarkable orthogonal ring of gas and stars exists in long-term equilibrium, sustained by the precise distribution of mass and angular momentum in the host galaxy and its dark matter halo. What makes the system especially compelling to astronomers is that it violates the common assumption of planar coherence in galactic structures. Most disk galaxies exhibit a dominant plane of rotation. Any misaligned or inclined features are typically short-lived due to differential precession and dynamical friction. However, the persistence of NGC 2685's polar ring over hundreds of millions of years challenges these models. It implies that either the mass of the ring is low enough to avoid significant back reaction on the central potential, or that the host's gravitational potential is sufficiently symmetric and spheroidal to support such a configuration over long durations. From a kinematic perspective, the galaxy exhibits two distinct and decoupled rotational systems. The main body rotates along its traditional axis, while the polar ring traces an entirely different orbital plane. High-resolution spectroscopy has shown that these two systems remain dynamically coherent, with minimal signs of warping or destabilization. This dual-axis rotation makes NGC 2685 a natural laboratory for studying the three-dimensional structure of galaxy potentials, especially in the context of triaxial dark matter halos. Furthermore, the polar ring is not just a passive relic. It continues to exhibit signs of star formation, as evidenced by H-alpha emissions and ultraviolet flux from young, hot stars. This ongoing activity confirms the presence of cold, dense molecular gas in the ring, material that may have originated from the captured dwarf galaxy or from cosmic filaments intersecting the halo of NGC 2685. The spatial distribution of this star-forming activity, often arranged in knots or arcs along the ring, suggests the influence of local gravitational instabilities, possibly amplified by the shearing forces between the ring and the host galaxy's gravitational field. The chemical composition of the ring also provides critical insight. Spectroscopic measurements reveal a lower metallicity in the polar ring compared to the central bulge, consistent with the hypothesis that the ring formed from the accretion of a less evolved, more primitive satellite galaxy. This chemical distinction serves as further evidence of the external origin of the ring and highlights the role of minor mergers in contributing not only mass but also chemically distinct stellar populations to larger galaxies. In terms of mass distribution, the fact that NGC 2685 maintains such a coherent polar structure implies a non-negligible influence from its dark matter halo. Numerical simulations have shown that flattened or oblate dark matter distributions can support polar rings by providing a stable, extended potential in which inclined orbits do not precess destructively. This connection between dark matter morphology and observable galactic structure turns NGC 2685 into a valuable tool for constraining the shape and extent of dark matter halos, information that is notoriously difficult to extract in more symmetric, conventional galaxies. Moreover, the polar ring may act as a tracer of the angular momentum history of the galaxy. Its inclination, precession rate, and mass distribution reflect the initial conditions of the interaction and the subsequent evolution of orbital parameters. By modeling these features in conjunction with observed stellar populations, researchers can effectively reconstruct the merger timeline of NGC 2685, offering a form of galactic archaeology that reveals the timing, nature, and impact of past accretion events. The implications extend beyond the galaxy itself. NGC 2685 serves as a representative of a broader, though rare, class of polar ring galaxies. These systems are exceptionally useful for studying the interplay between baryonic matter and dark matter, the mechanics of galactic warping, and the environmental conditions that allow multi-spin configurations to persist. Their rarity underscores the uniqueness of the conditions required for their formation, and their stability suggests that the universe is capable of sustaining highly nonlinear configurations when specific dynamical balances are achieved. Ultimately, NGC 2685 embodies the profound interconnectedness of cosmic phenomena. Gravity, angular momentum, star formation, and dark matter all contribute to its existence. It is a dynamic fossil, a relic of a complex interaction written in the language of rotation curves, metallicity gradients, and morphological asymmetries. In studying it, astronomers gain not only insights into one galaxy's peculiar structure but also broader understanding of the mechanisms that govern galactic diversity, stability, and transformation across the universe. NGC 2685, widely recognized as the Helix Galaxy, is one of the most extraordinary and scientifically valuable objects among the catalog of nearby galaxies. Classified as a polar ring galaxy, PRG, a rare morphological type, it defies the conventional structures observed in spiral and elliptical galaxies, offering a three-dimensional, multi-spin system that challenges traditional theories of galactic formation and equilibrium. What makes NGC 2685 especially significant is not only its rarity but its stability, its kinematic complexity, and the diverse astrophysical processes it encapsulates within a single system. The most striking feature of NGC 2685 is its orthogonally rotating polar ring, composed of stars, atomic and molecular gas, and interstellar dust. This ring orbits almost perpendicularly to the plane of the central lenticular galaxy. From a dynamical perspective, such a misaligned configuration presents a highly non-trivial case of three-dimensional angular momentum decoupling. In a typical system, differential precession would cause such a ring to warp, dissipate, or realign with the equatorial plane due to the torque exerted by the central potential. However, NGC 2685 demonstrates exceptional kinematic coherence and temporal longevity, maintaining the orthogonal orientation of the ring for over several 100 million years. Theoretical models and numerical simulations in N-body and hydrodynamic frameworks suggest that the long-term survival of the polar structure requires a quasi-spherical or mildly triaxial dark matter halo. A flattened potential would induce precessional torques that destabilize the ring, but in the presence of a near-spherical halo, the ring can stably orbit without significant warping. Therefore, the persistence of the ring in NGC 2685 provides strong empirical support for certain dark matter halo geometries, constraining both the halo's flattening parameter and its radial mass distribution. The prevailing formation scenario for the polar ring in NGC 2685 involves the accretion or tidal disruption of a gas-rich dwarf galaxy. Such events are supported by simulations that reproduce polar rings through off-plane mergers with inclined angular momentum vectors. During this process, the interstellar gas of the smaller companion settles into a polar orbit around the more massive host, cooling and collapsing to form new stars. The inner lenticular body of NGC 2685 remains relatively undisturbed, indicating a low-mass ratio minor merger, which limits structural damage while enabling significant mass transfer. Observationally, this hypothesis is corroborated by chemical and spectroscopic evidence. The metallicity of the ring is systematically lower than that of the host galaxy's central regions, indicating that the stars and gas in the ring originated in a less chemically evolved system. Additionally, line-of-sight velocity dispersion profiles and rotation curve asymmetry show that the polar ring is dynamically distinct from the spheroidal host, affirming the two-component origin theory. Despite the galaxy's overall quiescent appearance, the polar ring exhibits localized star formation, as revealed by observations in H-alpha, far ultraviolet, Galax, and infrared, Spitzer, WISE. These regions contain compact stellar associations and OB star clusters, indicating recent or ongoing episodes of star formation. The conditions in the ring are unique. The gas experiences differential shear, is subject to non-axisymmetric gravitational potentials, and exists in an off-plane geometry. These factors influence the gene's instability criterion, modifying the threshold for collapse and fragmentation. Furthermore, the ring provides a rare testbed for studying star formation under inclined, dynamically cold conditions, which are distinct from the disk instabilities found in classical spiral galaxies. Models incorporating feedback mechanisms from supernovae and stellar wind suggest that the evolution of polar rings involves a delicate interplay between self-gravity, cooling, and feedback-driven turbulence. In this context, NGC 2685 helps refine models of nonlinear star formation thresholds and star cluster survival in dynamically complex environments. Galaxies acquire angular momentum through a combination of tidal torques during the linear regime of structure formation and subsequent mergers and accretions. NGC 2685, with its two orthogonal rotation systems, serves as a direct observational probe of angular momentum misalignment in hierarchical galaxy formation. The ring preserves the angular momentum vector of the infalling material, while the host retains its original spin. This spin misalignment provides critical constraints on cosmological models of galactic assembly, particularly in the context of cold mode accretion and minor merger statistics in lambda-CDM cosmology. Moreover, the spatial distribution and orbital structure of the stars in both the host and the ring can be analyzed using integral field spectroscopy, e.g., SARON, MUSE, to extract 3D velocity fields. These measurements are invaluable for reconstructing the orbital anisotropy, potential shape, and merger geometry, providing a backward reconstruction of the galaxy's dynamical history. Perhaps one of the most scientifically valuable aspects of NGC 2685 is its utility in constraining the non-visible dark matter component. The polar ring acts as a tracer orbit, sensitive to the shape of the gravitational potential. By modeling the ring's stability, precession rate, and radial extension, astronomers can infer whether the halo is oblate, prolate, or triaxial, and to what degree. Unlike traditional rotation curve measurements confined to the galactic disk, the ring samples the potential in 3 dimensions, offering orthogonal leverage on the gravitational field. This makes NGC 2685 not just an astrophysical curiosity, but a powerful tool for dark matter cartography. Future studies using neutral hydrogen mapping, HI with VLA or MeerKAT, and stellar kinematics, with Gaia and ground-based IFUs, can further refine the mass profile and shape of the dark matter halo, which remains a key uncertainty in galaxy formation theory. NGC 2685 can be understood as a galaxy in transition, a dynamically settled system still bearing the scars and structure of a formative event. It encapsulates several processes critical to the evolution of galaxies in low-density environments: minor mergers, angular momentum acquisition, multiphase gas accretion, off-plane star formation, and non-coplanar stability. In doing so, it bridges the morphological gap between classical lenticulars and more chaotic merger remnants, demonstrating that even highly unusual configurations can reach equilibrium. Such systems may have been more common in the earlier universe, where gas inflow from the cosmic web often occurred along misaligned filaments. Therefore, NGC 2685 may represent a local analog to early universe galaxy dynamics, where rotation planes and inflow vectors were not yet aligned, and angular momentum was still being sorted across nested structures. By studying galaxies like NGC 2685, astronomers gain a glimpse into the nonlinear, stochastic nature of galaxy evolution, where form emerges not from simplicity, but from the resolution of chaotic interactions into lasting structure. NGC 2685 continues to intrigue astrophysicists not only because of its apparent uniqueness, but because it exemplifies how galaxies encode memory across billions of years. The interplay between the central lenticular core and the polar ring suggests a finely tuned dynamical architecture, where forces that normally compete instead coexist in a state of near-harmonic balance. Every orbit within the ring experiences both the pull of the central mass and the global influence of the surrounding dark halo, resulting in a motion that is neither chaotic nor trivial. This dance is further stabilized by the distribution of angular momentum, which must be delicately partitioned to prevent destructive resonances and warping. Such equilibrium is not accidental, it is the outcome of complex initial conditions, possibly only achievable through a very narrow set of merger parameters or cosmological infall angles. Simulations attempting to replicate this configuration often require precise initial orbital inclination, velocity dispersion, gas fraction, and host galaxy morphology. The success of these models is judged by their ability not just to produce a ring, but to maintain it with the correct kinematics and spatial extension over gigayear timescales. Deep imaging of NGC 2685 in optical and radio wavelengths reveals faint extensions and low surface brightness features beyond the main polar structure, suggesting that the galaxy's outer halo may still be perturbed or contain remnant material from the original merger. These features are vital, as they act like tidal fossils, recording the orientation and gravitational interactions of the past. Their morphology, luminosity profiles, and spectral lines help constrain the epoch and geometry of the encounter. Some of these arcs may be stellar streams or caustics formed by disrupted components of the captured galaxy, their motion slowly phasing into the broader halo. If properly traced and modeled, they could even allow a reconstruction of the original satellite's mass, orbit, and disintegration timescale. This turns NGC 2685 into a galactic time capsule, a structure whose current morphology encodes the detailed history of a minor but transformative merger. The polar ring also serves as a natural experiment in non-equilibrium star formation. The fact that stars continue to form in a structure that orbits nearly perpendicular to the galactic disk suggests that gravitational collapse and feedback operate effectively even under extreme geometrical and dynamical constraints. Local density enhancements, possibly induced by tidal interactions within the ring or by vertical compressive forces, may act as seeds for molecular cloud formation. These conditions differ significantly from those in spiral density waves or galactic bars, offering a complementary regime for testing models of cloud collapse, magnetic field alignment, and initial mass function variations. If star clusters in the ring are found to differ systematically in size, age spread, or chemical composition from those in the central galaxy, it may provide rare insights into how environmental factors shape stellar populations. The gas content of the polar ring, particularly the ratio of atomic to molecular hydrogen, remains a key diagnostic. High-resolution HI and CO mapping can reveal the thermal state, phase transitions, and turbulent spectrum of the gas, all of which influence its propensity to form stars. Measurements of line widths and velocity gradients across the ring may indicate the presence of shocks, shear, or hidden substructures like filamentary inflows. Such processes are relevant not only to NGC 2685 but to broader questions about how misaligned gas inflows behave in galaxies at high redshift, where cold streams were more prevalent. In this way, the Helix galaxy becomes a bridge between the calm, structured universe we observe today and the chaotic, rapidly evolving conditions of the early cosmos. Beyond its scientific applications, NGC 2685 challenges visual and conceptual expectations of galactic form. It invites a rethinking of what it means for a galaxy to be stable, for motion to be ordered, for structure to persist. Its morphology is not a product of simplicity, but of resolved complexity, a configuration that is inherently three-dimensional, layered, and historically contingent. Its beauty lies not in symmetry, but in the coexistence of seemingly incompatible motions, held together by the universal laws of gravity and momentum conservation. It is a structure that forces one to think in rotating frames, in evolving potentials, in histories that do not align but still intertwine. To observe such a galaxy is to witness a system on the edge of transformation, not in the midst of chaos, but resting in the delicate pause between dynamic phases. Whether the ring will dissipate, thicken into a diffuse halo, or eventually collapse inward to feed the central region remains uncertain. But in this uncertainty lies the essence of astrophysical inquiry, the ability to read motion as memory, to decode light into history, and to see in a single galaxy the echoes of formation, collision, and cosmic equilibrium. NGC 2685 is not static, despite its seemingly stable appearance. Beneath the calm rotation lies a subtle interplay of evolving forces, dynamical friction, gravitational torques, internal pressure gradients, that may, over cosmic timescales, alter its structure in imperceptible but accumulative ways. The polar ring, although kinematically stable now, is not immune to secular evolution. Star formation depletes its gas reservoir, stellar feedback injects energy into the surrounding medium, and slow interactions with the galactic halo can induce vertical thickening or gradual orbital decay. These processes are slow, occurring over hundreds of millions of years, but they act continuously. The present form of NGC 2685 is therefore transient, not fleeting, but evolving in a slow gravitational rhythm that defines its long-term destiny. Gravitational instabilities within the ring, although largely suppressed by its relatively low mass and high orbital velocity, may occasionally lead to local condensations, regions where the balance between pressure and self-gravity is tipped, giving rise to massive star clusters. Over time, these clusters may drift inward due to dynamical friction or migrate outward under the influence of radial pressure gradients. Their orbits, slightly perturbed by asymmetries in the mass distribution or halo shape, can begin to precess, tracing out rosettes in phase space that contribute to the diffuse stellar halo. This migration can seed the formation of faint stellar bridges between the polar ring and the central spheroid, slowly weaving the two components into a more unified stellar structure. On larger scales, the interaction between the polar ring and the hot, diffuse circumgalactic medium may also be significant. If the galaxy resides in a region with low-density intergalactic gas, as is often the case in field environments, then ram pressure stripping is minimal, allowing the ring to persist undisturbed. However, should NGC 2685 move through a denser medium, or experience infall into a group potential, even low-level pressure can begin to erode the ring's outer layers, peeling away cold gas and quenching future star formation. This would effectively fossilize the ring, transforming it from a site of ongoing stellar birth to a fading stellar relic, still rotating, still orthogonal, but no longer evolving actively. The central spheroid, meanwhile, shows little sign of disruption. Its stellar population, dominated by older, redder stars, rotates smoothly with low-velocity dispersion, suggesting that the core structure was already dynamically relaxed before the ring formed. Its morphology, close to that of an S0 galaxy, indicates an early cessation of significant gas accretion and star formation. Yet even here, the gravitational influence of the ring is not negligible. Over very long timescales,